Okay, today we start uh, the last chapter of the uh, material we will cover in this course: partial differential equations and Fourier series. We will cover basically two types of equations. Uh, we will study so-called heat equation and wave equation. Okay, heat equation is something like this, and wave equation is very similar, but there is this important difference that the derivative with respect to t is also the second derivative. Okay, so yeah, to solve these equations, we will use so-called the technique of separation of variables. It means basically you assume your solutions have the form uxy, uxt has the form of product of two functions. One function is a function of x, the other one is a function of t. This is what we understand from separation of variables. And when you plug this equation, this form into this, you will get ordinary differential equations in for x of x and t of t. We will solve each of them, and then we will combine the solutions, and then we will use Fourier series to write down the solution of the differential equation. But first, let us see what kind of problem we will obtain for x of x. That is the content of the first section, so-called 10.1 2-point boundary value problem. Okay, so what's a 2-point boundary value problem? It's an ordinary differential equation. So a second order linear 2-point boundary value problem is the form. It will be something like this. So a second order equation as usual. Okay, but instead of initial conditions, we have so-called boundary conditions. So we have an interval. At some point, the function takes some value. At the other point, the function takes some other value. So this is what's happening. I have some interval alpha beta, and I have prescribed values at these points, and I am looking for a solution. Okay, solution of the differential equation satisfying these initial conditions. So I look for solutions of this differential equation passing through these 2 points. Okay, that's why this is called 2-point boundary value problem. So you have an interval and its boundary points, and you ask a solution that passing through that passes through these 2 points. All right. Unlike uh, initial value problem, unlike initial value problems, uh, a 2-point boundary value problem may have no solution, a unique solution, or even infinitely many solutions. Uh, I mean, of course, even if P, Q, and G are continuous on the interval alpha beta. In case of initial value problems, if the coefficient functions p, q, and g are continuous, then for any initial conditions, you have a unique solution. But when it comes to 2-point boundary value problems, things might be different. Now let's see examples. First example is this one. So we are looking for solution of this 2-point boundary value problem. So my interval is 0 to pi. Okay, and we look for solution of the differential equation y double prime plus 2y equals 0 passing through the points 0 comma 1 and pi comma 0. All right, so how can we solve this? Well, uh, I know how to solve the differential equation, right? It's a constant coefficient equation, homogeneous. We write down its characteristic equation, which is r squared plus 2r plus 2. From this, we see that r1, 2 are just plus minus root 2. So the general solution of this equation is what? It is homogeneous, so it is just c1 times y1, which is e to the power r1x plus c2 times e to the power r2x. So it is just c1 times minus root 2x plus c2 times plus root 2x. And then we do what? Well, we just plug these boundary conditions and try to determine c1 and c2. Now plug the boundary conditions to efendim. Ee, evet. Özür dilerim. Şöyle diyeyim. C1 cosine root 2 x plus C2 sine root 2x. Yeah. To determine CIs. Okay, let's do that. So y0 equals 1. So when you plug 0, you get just C1 times C1 times 1 plus C2 times 0 equals 1. From this, we see that C1 is equal to 1. And the other condition, y of pi is equal to 0. When I plug this, I get C1 times cosine root 2 pi plus C2 sine root 2 pi equals 0. All right. From this, we see what? C1 is already 1, so C2 is then minus cosine root 2 pi divided by sine root 2 pi. So it is minus cotangent root 2 pi. So we get a unique solution, right? It is just C1, which is cosine root 2 pi minus cotangent böyle yazılıyor değil mi? Cotangent root 2 pi times sine sorry, burada ben garip yaptım. Root 2x olacak. Sine root 2x. So hence in this case we obtained a unique solution. Okay. Let's see another one. Y0 equals 1 and y pi equals a. So a is some arbitrary number. Okay. Solution. Again, we write its characteristic equation, which is r squared plus 1 equals 0. So r is just plus minus I. Therefore, y is just c1 times cosine x plus c2 times sine x. Let's plug the initial conditions. Y0 equals 1 implies what? C1 times 1 plus C2 times 0 equals 1. So again, we get C1 is just 1. And the second initial condition gives us what? When I plug pi, I get minus C1 plus C2 times 0 again is equal to A. So we see that C1 is equal to minus A. So I have these two conditions on C1. Well, you see, if A is not equal to minus 1, then we obtain a contradiction because C1 becomes 1 and C1 becomes not 1. So that's a contradiction. So in this case, then there is no solution. And if A equals minus 1, then C1 is 1 and C2 is arbitrary, so that we have infinitely many solutions. Y equals C1 is just 1, so it is okay. Let me write here. Y is equal to so cosine x plus C2 times sine x. C2 can be anything, okay? Can be anything. Okay. Let's see another one. So again, characteristic equation is just r squared plus 1. So r is plus minus I. Therefore, y is just c1 times cosine x, c2 times sine x. Let's plug the values. Y0 equals 0 implies c1 times 1 plus c2 times 0 equals 0. And this gives us c1 equals 0 this time. And y pi equals 0 implies c1 times minus 1 plus c2 times 0 equals 0. Well, this gives also the same thing, c1 equals 0. And there is no condition on y2. Hence, y equals c2 times sine x. c2 is any real numbers, therefore infinitely many solutions. Okay. Yeah, it is enough to spend this much time on this. When we come to separation of variables, we will get something similar to this last condition, infinitely many solutions, and we will see what happens. Okay, now okay, let me pass to directly 10.5 separation of variables. And let's consider heat equation. I'm sorry. Okay. Peki, heat equation. So, we will heat equation in a road theme. So this is kind of one-dimensional heat equation. So consider the following uh, boundary value problem. We will call this a boundary value problem. So alpha squared uxx is equal to ut. This is the heat equation, okay? It's a partial differential equation. And then we have actually an initial condition. This is initial temperature distribution. Temperature distribution. And then we have boundary conditions. Okay, boundary conditions. In this case, there homogeneous boundary conditions. Let me explain what is this equation. I have a rod. This can be, for example, a cylindrical metal rod, okay, of length L. So let's say this is the x-axis, okay. And what we know is that at time zero, so u x t is the temperature at position x at time t. Okay, so at any point x here and at time t, uxt is the temperature at that point and at that time. So what is this ux0? That's the initial temperature distribution. Why it is called initial temperature distribution? Because you see, when you plug T equals 0, it gives you the temperature at any point. Okay, at this point the temperature is f of 0, and then f of temperature at this point at time 0 is f of 1, and so on. Okay, so f of x gives us the temperature of the rod at time 0 at any point. That's why we call it initial temperature distribution. What about these two conditions? Well, these two tells us the following. Both of this end, when x equals 0, I am at this end. When x equals L, I am at this end. The temperature of the rod is kept at 0, okay? So that's a condition. You may think of, putting large ice cubes to both ends of this rod at temperature 0. So at all times, the temperature at these two ends are kept 0. Okay. Since these are 0, we call this problem a homogeneous two-point boundary value problem. Okay. So we have homogeneous boundary conditions, and therefore this is called a homogeneous. That's why the problem is called two-point homogeneous two-point boundary value problem. Okay, for heat equation. Okay, well, how can we solve this? How to solve? We make use of so-called the method of separation of variables. This is not a method to solve only heat equation. It can be used for many other partial differential equations. For example, for the wave equation, we will use the same equation. For Laplace equation and for more general equations, it can be used. And the idea is this. What's the idea? Look for solutions of the form u equals uxt that can be written as a function, a product of uh, a, the product of a function of x and a function of t. Okay, so for this equation, I look for solutions of this type. Okay, let's see what happens. Well, I will take this and plug into the equation. All right, so for that, let me write it here again. uxt equals x of x and t of t. To plug this into the equation, I have to take derivatives. So what is u sub x? Well, I take derivative with respect to x. This is a product of two functions. One is a function of x, the other one is a function of t. When I take derivative with respect to x, I regard t as if it is a constant, so I just take the derivative of the function of x. And derivative of this with respect to x is just x prime x, and then I have t of t. What about the second derivative? Well, I'll do this one more time. I just take derivative with respect to x, therefore I just get x double prime times t of t. What about the derivative with respect to t? Well, this time I'm taking derivative with respect to t, therefore I regard x as if it's a constant. Therefore, this will be just x of x times t prime. Okay. Now, plug these into the equation to get, well, let's see what we get. So our equation was alpha squared uxx equals ut. So this gives us what? This gives us alpha squared uxx. Uxx is just second derivative of x times t, and that's equal to u sub t. U sub t is just x times t prime. Okay, and then we do what? We separate x and y variables, and let's see what we get. So we have x double prime over x and uh, t prime over t equals, okay, alfayı nerede tutayım? Alfayı şurada tutayım. No. Okay. Yeah. Okay. Let me just write it this way. Yok, şöyle yapayım. Pardon. Şu alfa square'i buraya alayım. Tamam. Şimdi observation şu. X x'in fonksiyonuydu. T de t'nin fonksiyonu, değil mi? Dolayısıyla sol taraf, therefore the left hand side is a function of x only and the right hand side is a function of t only, right? Note that the left hand side is a function of x only and the right hand side is a function of t only. Here alpha is just a constant, okay? It's a constant. Well, if I have functions of independent variables x and t, and these two functions are the same, right? So I have a function and this is equal to function of some other variable. You see, I can change x and keep t constant. So the left hand side changes while the right hand side stays constant. This means that actually the function f of x has to be constant, right? Because even if I change x, since I don't change t, this value doesn't change. And therefore, this f of x actually has to be a constant function. And similarly, of course, g of t has to be a constant function. So if I have this, there is only one possible solution. This implies that both terms are constant functions. Okay. Let's say this constant function, it's a common function, right? Both of these are constant functions. Let's say this is equal to minus lambda squared. Minus lambda, sorry. We will see why we choose minus lambda, where lambda is a constant. Well, so I have two equations then. So we get two equations. One of them is x double prime over x is minus lambda, and the other one is t prime over t 1 over alpha squared is equal to minus lambda. Let's start with the first one. So x double prime over x equals minus lambda. Let's see, uh, how can we solve this? Well, this gives us what? I just take x to this side and then take lambda x to the other side, and I get this. It's a constant coefficient. Homogeneous equation. All right. And the other one is a is what? It is lambda alpha squared plus t. Another constant coefficient, also a constant coefficient equation. Actually, it is linear, right? I mean, a first order equation. This is second order, but this is first order. All right, so I obtained two equations, and I know how to solve these, right? I know how to solve these equations, but one has to be careful. Here, we don't know what lambda is, okay? Even though this is a constant coefficient equation, we don't know what lambda is, okay? And that will be very important soon. How? Now, consider the boundary conditions, homogeneous boundary conditions. Okay, I had these two conditions. U 0t is equal to 0 and U LT is equal to 0. Okay, what about boundary conditions? Well, I have this. I assume that U xt is a function of x of x and t of t, and we have two boundary conditions. U0 t equals 0 and uxt equals 0. Well, this gives us what? X of x times t of t x of 0 times t of t is 0, and this gives me x of L, x of L times t of t equals 0. Well, if x of 0 or x of L are not 0, then t of t would be 0. Note that if x of 0 isn't 0 or x of L isn't 0, then the function t of t would be identically 0, right? Because this constant times the function is 0. And thus uxt would be just the 0 function. Okay, 0 for all x and t. But that's not interesting, right? And that's not actually something we want. Why is that? You see, our problem is this, and u equals 0 doesn't satisfy the initial temperature distribution. It satisfies the differential equation and the initial conditions, but doesn't satisfy the initial temperature distribution condition. Therefore, u equals 0 is not, something would like to have as the solution. So we would like to have some other solutions, okay? And clearly, it shouldn't be the solution. Why is that? Because you heat up the, let's say, metal object bar, and then you let it cool down. And as time passes, the temperature changes, on the road. However, it is not constantly 0, right? It will change in time. So, to avoid obtaining this trivial solution, I have to assume that x of 0 and x of L both non-zero. Hence, to obtain non-zero solutions, we must let x of 0 equals 0 and x of L equals 0. Well, now let's see what we have. For x, I have a differential equation. Where was it? It is this equation, a constant coefficient equation. And I have two initial boundary conditions. So we obtained a boundary value problem. Okay. Hence, thus, for x of x, we have a 2-point boundary value problem. What's that problem? Let's write it down. It is x double prime plus lambda x equals 0, x of 0 equals 0, and x of L equals 0. And we should keep in mind that lambda is a constant, but we don't know its value, okay? So let's see what we will have. Now let's try to solve this equation. Solve the above problem. Let us solve the above 2-point boundary value problem. Okay, how can we solve this? We write its characteristic equation as usual. So it is r squared plus lambda equals 0. From this we get r squared is minus lambda. All right, now we have cases, right? Case 1, lambda could be negative. Well, in this case, r squared is minus lambda is positive. Therefore, r1 and 2 are just the square root of this positive number, plus square root and minus square root. So x of x would be just, okay, let me just write it this way, minus, okay, let's say r1x plus c2 r2x. r1 and r2 are just plus minus square roots, okay? All right, how can I find c1 and c2? Well, let's use the initial conditions. Sorry, use the boundary value, uh, boundary values. Okay, so what are these? X of 0 equals 0. So if I plug this, we get what? C1 times e to the power 0 plus C2 times e to the power 0. Well, they are both 1. So from this, we see that C1 is equal to minus C2. And the other one is L is 0, X of L is 0. So from this, we see that C1 times e to the power minus R1L plus just R1L, C2 times e to the power R2L equals 0. But R1 and R2 are just, right, they're negatives. So I have this. And C1 equals minus C2. So if I plug this, I get C1 times R1L minus C1 times e to the power minus R1L, right? Equals 0. So in C1 parentheses, actually C1 R1 to the power L parentheses, I have 1 minus okay, 1 minus e to the power 2 R1L equals 0. Well, R1 is okay, so 2 R1L is not 0, is not 0. Therefore, e to the power 2 R1L is not equal to 1. Okay, and this implies that this number is not 0, right? Because this is not 1. So 1 over that thing is not 1. So this is not 0. Well, this implies C1 times e to the power R1L is 0. But e to the power R1L is never 0. And therefore, C1 is 0. Well, C1 and C2 were almost the same. This implies C2, which is minus C1, is 0. Therefore, hence, x of x is 0, the only solution. So we didn't get anything interesting in this case. Second case, lambda equals 0, right? First, here I assume that lambda is negative. Now we assume lambda is 0. Okay, so r squared is minus lambda 0. Therefore, r is just r1 and 2 are both 0. So what are the solutions? Y1 is just e to the power r1 x, which is just 1 because r1 is 0. Y2 is, since it is a repeated root, x times y1, so it is just x times 1, which is x. Therefore, these are the solutions. Therefore, the general solution is just C1 times 1 plus C2 times Y2, which is X. So C1 plus C2X. Okay. To determine C1 and C2, we just use initial boundary conditions. What were the boundary conditions? X of 0 is equal to 0. Well, this implies C1 plus C2 times 0 equals 0. Well, this implies C1 is 0. And X of L is equal to 0. That would give C1 times C2 times L is equal to 0. But C1 is already 0. So this gives C2 times L is 0. L is the length of the metal object. So L is positive, of course. This would give C2 is 0. So both C1 and C2 are 0. Therefore, X equals X of X equals 0 is the only solution. Of course, we don't want the 0 solution because in this case, right? So if this is the only solution, then what about U? U is just X times T. X is 0, therefore this is the 0 solution. And that's not interesting, okay? So both of these cases gave us trivial solutions which are not interesting. The third case is that lambda is positive. So we have r squared is minus lambda is this time negative. So r is plus minus square root of lambda times I. Okay, so minus 1 goes out as I from the square root. So r1 and 2 are just these numbers. Let's call the square root of lambda to be mu, which is a positive real number. So r1 is just mu times I and r2 is minus mu times I. And what about the solution then? X of x, c1 times cosine mu x plus c2 times sine mu x. All right, and then we do what? We apply initial condition, boundary conditions. Apply the boundary conditions. X of 0 equals 0. Well, if I plug this, I just get C1 times 1, C2 times 0 equals 0. This gives me again C1 equals 0. And X of x becomes what? X of x becomes C2 times sine mu x. And we use the second initial condition. X of L equals 0. And let's see what this will give us in the second hour. Let me stop here.